Okay, first objective here. Seems like, oh my gosh, just went through 20 minutes of video, haven't even gotten to the first objective yet. Well, here it is. So here we're going to be able to use a graph. I have a picture of a graph. I'm going to use that to help me cheat. To help me find some zeros of polynomials. So in the picture here, you got this guy who's trying to wade across, I think it's called fording, going across a river. So think of the river as the x-axis. And if you're on the river, you're on the x-axis. If I'm on the x-axis, that's one of the zeros, and that's what we're looking for. That's what we're looking for. If I have a picture of the graph, if I see a dot on the x-axis, that's one of my zeros. Maybe it's on an exact number, like take a look at the flipping math logo that's right up here. If I knew that this number was exactly the number 1, well, there I go. I have my answer. I could put that into the equation, or I can synthetically divide by that number and then get the rest of it that's left over. And that's a good place to start. Okay. So the first way to facilitate, that just means to make it easier. The first way to make this easier is to look at a graph and check to see where it crosses the x-axis. So since the zeros are the same thing as the x-intercepts, if I can find myself a place where it crosses the x-axis, this little dot, there's a place to start. So I would have listed out with the rational zero theorem what are my possibilities. And if I look at the graph, it looks like this is at 1, 2.5. Looks like it's at 2.5. If 2.5 was part of my list, and of course it would be in fraction form, probably 5/2, yeah. If that was in my list, then I could synthetically divide by that and then get the rest of the answer that I could use and try to factor it, okay? So let's give this a try on this first equation. So I've got, and this I believe is the same one looked at in the opening or the introductory video, where we knew that x could possibly be equal to plus or minus 1, 2, 7, 14, plus all of them divided by 2. Well, all of the odd ones divided by 2, so 1/2 and 7/2. Okay, so if I look at my graph, it looks like it crosses right here at exactly 2. So of course I could synthetically substitute 2 in there, see what's left over. There's one right here. That might be, if you look at the scale of this, that might be the number -1. And this one is in between. This looks like -3 and -4. That's the one I'm going to do just because I want to make this so that you can see an example of me using a fraction here. So in between the 3 and the 4, that would be the 7/2, specifically a -7/2. So I'm going to put that outside the box, -7/2, and then I got a 2, a 5, -11, and -14. Bring down the 2.
Multiply times 7/2, the 2's will cancel and it'll just be -7. Add them, -2. Multiply them, the 2's would cancel, negative times negative makes it a +7. And I get a -4 here. Multiply a 2 will go into the 4 2 times, negatives will cancel, blah, 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 14. 0.
And there we go. I've got my first one. So what I have left over here is 2x squared minus 2x minus 4. Now if I'm going to find the zeros for this, I set it equal to 0. I notice that they're all even, so I could divide by 2. So x squared minus x minus 2. And then open up some parentheses and stuff. X and x, it has to be 1 and 2. It's the only thing that can work. And it's got to be a negative and a positive here. So all of my answers, all my zeros go like this. X is equal to the original one that I divided by, -7/2. From the first set of parentheses, -1. And from the last one, a +2. If I look at my graph, of course, that's exactly where it crosses the x-axis, all of those places. And I know in the comments you're going to go, why didn't you just choose the number 2? Well, I could have. I just wanted to show you that I want to show you an example with a fraction, because, you know, sometimes fractions scare people away. And they don't have to. Anyway, so I call this method cheating because of this. Usually, we're looking for zeros to help us graph a polynomial. In other words, whenever I go to graph it, I want to see we're going to cross the x-axis. Okay? But now we're using a graph to help us find the zeros. It seems a little backwards. I need to use a graph to find the zeros, but I'm using the zeros to find the graph. That's why I say it's a fine example of some circular logic. Anyway, it's teacher sanctioned and you get to use it. I may give you a picture of a graph, or you may have to plug it into your calculator, y equals, type in your equation to see where it might touch the x-axis. Okay? Give it a try in the next couple of examples. Next video probably.